Hey everybody, so there was a example problem we didn't get to last time at the end of lecture 16, so let's look at that real quick. Let's work through this and then we'll continue on with the rest of lecture 17. So again, this is intro to the second law of thermodynamics. This is a heat pump problem, right? And if you remember last time we talked about, we introduced concepts of heat engines. So we said a heat engine is a device that takes heat in, puts a little bit of work out, rejects the remaining heat. If you look at the first law for that, the net work out is equal to the difference between the heat in and the heat out. The efficiency ends up simplifying as the net work out, made a mistake, net work out divided by the heat required to do that is equal to, and it's also equal to 1 minus QL over QH. So these, where we can write this efficiency or the performance as a function of the ratio of heat transfers, is going to become more important a little bit later. Okay. We also talked about the refrigerator, a device that removes heat from a low temperature source and rejects that heat to a high temperature source, does so by consuming just a little bit of work. First law, work in is equal to basically the heat out, the net heat out, and the coefficient of performance for a refrigerator. What you want is you want the heat from the low temperature source divided by the work in, and we can massage that into this 1 over QH over QL minus 1. Now, the reason I went through this is because the last thing we did was the heat pump. We did this one kind of quickly, but you can see here the heat pump, that's a device that also removes heat from a low temperature source, puts heat into a high temperature source. The goal of a heat pump is we want to borrow the heat from an outside low temperature source and move it to a high temperature location, like inside of our house. So we want to borrow heat from outside the house, put it inside the house. We're basically going to pump it with just a little bit of work in. Same first law diagram, add the work in minus the heat out, add the heat in, that equals 0 for a cyclic system. The coefficient of performance for this heat pump is going to be QH, what we want, this quantity, divided by what we have to do to get it to work in. And we can massage that again down to this function of the ratio of heat transfers. Now, so let's look at this heat pump problem there. Pull our notes from last time. I have those readily available. I have some of these equations memorized. I can only derive them quickly, but I'm going to have that guy readily available for me here. So we've got a residential heat pump using refrigerant 134A. You can see the diagram here. They've given us the inlet and exit conditions of the condenser unit. They've told us the R134 comes in at 800 kilopascals and 35 degrees C, exits as a saturated liquid at 800 kilopascals, constant pressure. That's pretty typical. We want these to be as close to constant pressure as we can get. The power input there, and I couldn't put dots on these very easily. That's a W dot and an M dot because those are per unit time. So the power input to the compressor is 1.2 kilowatts. The mass flow rate is 0.0818 kilograms per second. We want to find the coefficient of performance for the heat pump as well as this QL. Let's draw this diagram with you real quick here. So again, it's a heat pump. So we got an example problem here. I've got this heat pump. We'll draw real quickly here. I've got this condenser on top, rejecting heat to a high temperature source. It's being fed by a compressor. I like to draw kind of this turbo compressor where I've got a power input of 1.2 kilowatts. So I'm drawing this so you could draw this in your notes as you go along, because just sitting here watching me do this, probably I don't know that you're going to get a whole lot out of that. But if you'll actually draw this along as you go, you'll trick your mind into thinking this is important, and maybe it'll remember it. That's kind of what we want to do. So I'd suggest draw it, but do it as you like. We've got a power input, 1.2 kilowatts, And so these are going to be dots. I'm going to put dots on these because this is per unit time. Let's work these per unit time as well. So I can find the rate of heat rejection to the high temperature source, the rate of heat removal from the low temperature source, and then we've got this magic expansion valve process. We talked briefly about this in the last period. The idea is if I've got a high pressure fluid, I allow it to expand, go to a lower pressure, the temperature will drop, and the goal is to get the temperature to drop so far that the refrigerant at this point in the cycle is so cold it will absorb heat from the lower temperature colder source. Now they've told me that I've got 800 kilopascals fairly constant throughout the condenser. They've told me that it's coming in at 35 degrees C and it's going out as a saturated liquid. Okay? They want us to find coefficient of performance for the heat pump. They also want us to find the rate at which heat is being removed. Well, the reason I've got my review notes here is for these expressions. So we can find the coefficient of performance of a heat pump by definition is just this, we can say Q dot H over the power input. Or we could find it as 1 over 1 minus Q dot L over Q dot H. Either of those work. I don't know if that's going to help us. Right? Because I don't know Q dot L or Q dot H, either one. I need to find those. So we say, all right, well, what else can we find? And by the way, we also know first law for the heat pump tells us that if you look at the first law for the whole thing, we can say, well, the power input minus the rate of QH plus Q dot L, that's equal to 0 because it's a cycle. So I just need one of these heat transfers. If I can find one of these heat transfers, I can find the COP and I can find the other unknown heat transfer. So I need to see, well, what can I do to find one of these heat transfers? Well, one of the things I always like to ask is, what is a system? Right? This first law is derived with the entire heat pump as my system. A common thing we'll do in these problems is we'll say, what about the first law for one of these units? Specifically, the condenser. So if I do a first law analysis on the condenser, which means what crosses the boundary, well, I've got mass, and heat. This is a steady flow control volume, meaning that minus Q dot H, we've got one inlet, one outlet, so that's a chapter 5 problem for us. That's plus m dot times H1 minus H2 is equal to 0. That's assuming I'm calling this 1 and this 2. This is the difference in the energy of the mass in and the energy of the mass out. Okay. Can I find these H's? Well, sure. I know pressure and temperature here. I know pressure and saturated liquid there. So then I can just go look these up. Okay. So far, so good. This is page number 1. And I can set this aside. So let's do page number 2 here. So what do I need to know? Well, if I can find, because remember, if I can find QH, that goes here, then I can find COP, and I can go here and find QL, the two things that they're asking for. So this thing starts falling apart pretty quickly. So let's find properties. So again, given pressure of 800 kilopascals, this is R134A. I would just need property tables for R134A, which we have in our text. The inlet temperature of 35 degrees C. That'll give me H1. And then same pressure at the outlet, 800 kilopascals. It's a saturated liquid. Our quality is 0 at the outlet. That's a shorthand way of writing that the quality is 0. The X value represents the amount in the vapor phase. I'm saying 0% in the vapor phase. Alright, let me grab my book. Where am I at on time? Loud pop here, sorry. Okay, I got a minute or two. Let me get my book. Sorry, I didn't have it ready. Okay, I apologize. My book was in the other room. I'm back now. Okay. Got R134, metric units. Looking up properties. Let's see if I can get this on the camera here. Alright. So R134A. So go to your property tables here. Loud pop here, sorry. I've got 0.8 megapascals. I've got 800 kilopascals. It boils at this pressure at 31 C. We're at 35. So I'll need to interpolate between these two H values. These are my H values. So my H value is going to be about 270 something. I think I've got these numbers here in just a second. So that'll give me my H value there at the inlet. Okay, because I've got 35 degrees. I don't have a row in my tables for 35. I'll have to interpolate that. But I do know then I've got saturated liquid at the outlet. So I've got 800 kilopascals, R134, 800 kilopascals, saturated liquid. Enthalpy at the saturated liquid, the X is going to be 95.48. So H1 we said is going to be probably about 270-ish. We're going to look up an exact value or interpolate an exact value here in a second. H2 for saturated liquid. In our tables we're getting about 95.48. Alright. Now to interpolate this guy, I've got, so H1, so it's going to be minus HA divided by HB minus HA is equal to, I've got 35 degrees. I've got a row for the saturated temperature, that's 31.31. And I've got a row for 40. So it's 40 minus 31.31. Okay? And H for the saturated row is 267.34. That's for row A, and then HB is 276.46. Both of those are kilojoules per kilogram. Now I'm going to stop there. I'm about to hit my 15-minute break. And we'll do the magic calculation and we'll be back.